Okay, so then we are going to start today. So last week we introduced the particle filter, or the basics of particle filtering. So how to do recursive Bayesian state estimation in the context of non-parametric distributions. And we especially looked into the sample-based representation. The idea was to use a set of samples to represent the state space and the distribution over possible states. And we can see every sample as a post hypothesis. So every sample represents one possible state the system might be in. And then the probability distribution is given by a sum over the states of those samples together with a weighing term and a Dirac distribution in the state of these samples. And the key advantage of these sample-based representations is that we are very flexible with the type of distribution we can represent. So we are not restricted to Gaussian distributions, for example, as this was the case for the Kalman filter or extended Kalman filter, but we can easily represent multimodal distributions in here. And today, I would like to look into the SLAM problem. So how can we actually address the SLAM problem using particle filters? So just as kind of a two-slide repetition of the particle filter, what we discussed last week. So the particle filter is a non-parametric estimation technique. That means I don't have a parametric form, like a Gaussian distribution, for example. So distribution in parametric form, which I use to represent my probability distribution. But I use samples, or weighted samples, and kind of the number of samples that fall into a region of the state space is proportional to the probability of that area. That's kind of the key idea behind that. What we haven't discussed in detail here, but what I at least said last time, is that the particle filter is very well suited for doing state estimation in low-dimensional spaces. If we go to very high-dimensional spaces, that is more challenging. Why? The reason is that I need a sufficient number of samples to cover, let's say, the areas of high likelihood or regions of high likelihood in my state space. And if I have a high-dimensional state space, I need a huge number of samples. And therefore, these approaches work well in low-dimensional spaces, 3, 4, 5, 6 dimensions, something along these lines. But they do not work well in whatever 100-dimensional spaces. That's kind of one of the problems of the particle filter, that it gets computationally so inefficient because I need such a huge number of samples that the approach simply doesn't scale to higher dimensions, at least not in its standard direct form. The particle filter itself consists of 3 steps, which we discussed. The first one was the sampling step, where I draw samples from my proposal distribution. The second step was an importance weighting step, which was the result of the importance sampling principle, which tells me that if the proposal distribution is not the distribution I want to approximate, and this is typically the case, then I need to do a correction step, so to say, and compute an importance weight that accounts for the differences between the target distribution, so the distribution I want to approximate, and the proposal distribution, the distribution from which I've drawn my samples. And the last step was the resampling step, which kind of redistributes the samples and there's a high likelihood that a sample with a low probability is replaced by a sample with a high probability. So it's kind of this survival of the fittest-like principle in order to concentrate the samples in the likely areas of my state space. If we look to that in algorithmic form, we had these 3 steps here. The first one was I draw a new sample. So this is the J sample at time t from my proposal distribution pi. And for the localization example, we used the odometry motion model to generate the next generation of particles. So we say, how did the pose of the robot evolve given that we executed a command? That's what we use the proposal distribution for. And that will also be the proposal distribution in the SLAM context, as we will explore that today. And then the second step is the importance weighting step. This was a direct result from the importance sampling principle, which says that if I draw samples from an arbitrary proposal distribution, but I want to approximate a target distribution, I need to assign a weight to each sample, and the weight is given by the target divided by the proposal, both evaluated in the location of the drawn sample. So a sample where, for example, the target distribution has a very high likelihood and the proposal distribution very low likelihood, this gets amplified by getting a high weight. This just accounts for the differences between the target and the proposal. And the last step was the resampling process, with just drawing samples with replacement. So I draw sample I proportional to its likelihood. I do that with replacement. I simply draw J samples. And that's the resampling process. And after resampling, all the weights are set to 1 divided by n, because then they are, again, the locations of the samples are distributed according to the target in the end. That's what I wanted to have. So this was the key steps of the particle filter, which we discussed last time. And what I use is a set of weighted samples, x and omega, in order to, or w, x and w here, in order to represent the state and the weight. And this is my sample set. And if we now think about the SLAM problem, so we move away from localization, where the state space was an x, y, theta location, and we move towards the SLAM, where we want to estimate the position or trajectory of the robot, and together with all landmark locations or the whole map, then our state space moves from a 3-dimensional state to a high-dimensional state space. So we have here the poses where the robot has been, and all landmark locations. So in the beginning, and for localization, we just had x, y, theta, so a 3-dimensional state space. And here now we have a much higher dimensional state space. So as I said before, the particle filter is an effective representation for low-dimensional spaces. But this turns to be not the case in our setting over here. So this is a high-dimensional state space. If I have, let's say, 1 million landmarks, and the long trajectory of the robot, I have easily a 2 million plus the length of the trajectory dimensional state space, which is orders of magnitudes larger than what a particle filter with a finite number of samples, or with a number of samples that I can actually represent in a computer system, can actually handle. So there's no way of applying a standard particle filter sampling the overall state space. That's kind of one of the key limitations why it actually took quite a while until people discovered a way, or not discovered a way, but found a way to use particle filter-based SLAM, or build particle filter-based SLAM system. And the key idea is, let's have a look to the individual state variables that we have in our state space, and let's see if we can actually exploit a dependency between them. So if there are a dependency between the poses and the individual landmark locations that we might exploit, what do you think? If I ask this question, the answer is too obvious, but then the next answer would be, what is a possible dependency we could exploit? So we have the positions of the robot during data acquisition, x1 to t, and we have the locations of all m landmarks. It's a high-dimensional state space. We want to cover this state space by samples, but we cannot cover the full state space using a sampling technique, so we have to do better. So do you see any way of exploiting a dependency between those variables to do that in a more efficient way? Is there any dependency you know between these variables?
No.
Which one?
You can assume they're independent.
You really think the poses of the robot and the landmarks in the environment are independent of each other?
Not the pose with the robots, the landmark with each other are independent.
I strongly disagree with that. Otherwise, this whole lecture would not take place, because then would be two separate estimation problems, and simultaneous localization wouldn't exist. So there must be something else.
Yeah, the robot pose is surely dependent to the maps to the landmarks,
Mm-hmm.
and the landmarks to each other also.
Yeah. If you think about the lecture on grid maps that we had last week, what dependency did we exploit in there?
I wasn't there.
Okay, anyway, the others? So what was mapping, the grid mapping approach that I presented, the work of Moravec and Elfes, was done in the context of grid mapping, but that shouldn't bother us, just consider that was a map. Why was this so easy to compute? This is true. We assumed independence of the grid cells. This is absolutely right, but that was not the point I want to nail down here at the moment. There was another strong dependency that we exploited.
Because the map is static?
Yes, but we talk about static maps here as well. So the key underlying assumptions of this mapping algorithm was, once I know the poses of the robot, mapping is easy, right? So if we know where the robot is during data acquisition, mapping is easy. So that's exactly what we learned. Given we know the trajectory where the robot was during data acquisition, estimating the map is easy. So if I know where the robot is at every point in time, there is no post uncertainty of the system, and I just can continuously measure the landmarks and update their belief. There's not this mutual dependency between the pose of the robot that impact the landmarks and vice versa. I can simply easily break that up. So the key idea, what we now want to do, is to use a particle filter to only represent the poses of the robot. Then every sample is an individual trajectory estimate. Sample 1 says, okay, the robot went along here on this path. Sample 2 says, okay, the robot went here, but it went a little bit further there and then turned around. Particle number 3 says, okay, I walked down for a longer period of time and then turned left. Every of those samples assumes that it did the right job. That was the key idea of the particle filter. Every sample says, I did the right thing. So as a result of that, I can say, okay, one option is particle 1 did the right job. If particle 1 did the right job, the world will look like the trajectory of particle 1 applying mapping with known poses. Or particle 2 was right in estimating the current trajectory. Then I take particle number 2 and do mapping with known poses using the trajectory of particle number 2, and so on. So as a result of that, I have a distribution of possible maps that are generated conditioned on the samples, on the poses, sorry. So the key idea is now to use a particle filter to represent only the trajectories that the robot have taken, and then for every sample build an individual map using mapping with known poses, and say, if the trajectory of particle 1 was the right trajectory, then the world looks like this. Or particle 2 did the right job, then this was the trajectory, and then the map looks like the map that is generated using the trajectory of particle number 2, and so on. So compared to localization, where I kind of maintained a single x, y, theta location for every sample, I now have a trajectory, and to every trajectory you can see kind of there's attached a map. And this map is a result of that trajectory. And that's exactly what the particle filter, the so-called Rao-Blackwellized particle filter is doing. And this technique is something which is called Rao-Blackwellization. So, and mathematically, it's a very trivial factorization. That's just kind of the definition of the conditional probability that is exploited here. So given that I want to represent this distribution about, let's say, two random variables A and B here. And P of B given A, so this part over here, can be computed very efficiently. So given I know A, I can compute B easily. If this is the case, it can make sense to say, okay, let's represent only A with samples, and then for every sample just compute P of B given A, given that I take exactly the state of A, which the sample told me. So for what does it mean for us here? For us it means A is the trajectory or the poses of the robot, and B is the map. So I say instead of computing P of A and B, so P of the robot's poses and the map, with particles, I say, okay, let's take only P of A, so the trajectory of the robot, use samples to represent that, and then for every sample, compute P of B given A, so the likelihood of the map given the trajectory in an efficient manner. That's kind of the key idea behind that. As a result of that, I need the samples only to cover the likely regions in A and not in A and B. And especially if we now think about A is low dimensional and B is very high dimensional, this is a great advantage. And that's exactly the key idea what the Rao-Blackwellized particle filter for mapping does. So it starts out with the probability distribution about the poses and the map. So these are now M landmarks, capital M landmarks, given my observations and given my movements. It's kind of the standard thing. What it now does, it just factorizes this belief into two terms, namely P of x given these quantities here, so the observations and the controls, times P of m given x, the observation and the controls. So just split that up, just applying the definition of the conditional probability to separate that term into, so if here P of x given the observations and the controls times P of the map given x, the observations. In theory, you have the controls in here, but we can actually ignore them if we know the poses. It's kind of so there are two steps in here. So ut should be u1 to t could be in here, but I can neglect that because once I know the poses, I'm not interested in the odometry commands anymore. So we have now two posteriors. The first one is path posterior, which estimates what's the trajectory that the robot took. And the second is a map posterior that depends on the possible paths that the robot has been taking. Okay? Okay, good. So the question is, how can we compute this term efficiently? And this is, again, as I said, mapping with known poses. Okay, so we discussed mapping with known poses in the context of grid map, but not that much in the context of, we did in the beginning in the EKF. Let's have a very, very quick look how we could do that. In order to do that, let's have a look to the graphical model that underlies this process. So this is a graphical model you have seen in probably the first lecture of this course. So we have here the poses of the robot, x, which I want to estimate. I have the landmarks down here, the observations, and the controls. So what this says is read these errors at influences. So you say xt minus 1 influences xt as well as ut influences xt. So this is exactly the motion model which sits in here. It's p of xt given xt minus 1 and ut. And these errors show kind of a direct dependence. The same holds. The current pose has an impact on what I'm going to observe, and also the location of the landmark has an impact on what I'm going to observe. This is how you can read that. And you can use these graphical models to, or in this case a Bayes network, to also express conditional independence or independence of variables. Okay, if we now say we know the poses of the system, right? That's what this in the, so we want to estimate this guy over here. We assume that we know all the poses. So all these guys up here are known. So all these variables are known. And as a result of that, you can't find any path from any landmark to another landmark which doesn't go through these known variables. So there's no way kind of to reach from M1 to go to M2, or from M2 to M3, or from M3 to M1, throughout passing through these known poses. And if this is the case, these variables are independent of each other. So what this results in is these landmarks are all independent of each other, given we know the poses of the system. It's not the official formal definition of independence in those graphical models, but for now, I would like to stick with this very simplified form. So at least if all passes from one variable to another variable are blocked, so to say, by a known quantity, then these variables are independent given these known quantities. This is exactly the case here. So there's no path from one landmark to another landmark given I know the poses. So for this posterior over here, I can say all the landmarks are independent of each other because I know where the system was at every point in time. Okay, so landmark variables are kind of disconnected, so they're independent given the robot's graph. Okay, so I know that here these landmarks are independent of each other now, given the poses. So I can split that up into a product of probability distributions over the individual landmark locations. So this turns into a product over m landmarks, p of mi, so there's not the individual landmark, given the poses and given the observations. In which way is this a dramatic simplification to go from here to here? Why is it substantially easier to do it this way compared to that way? Yeah.
We can compute each landmark separately.
Exactly. And if you think about EKF, for example, to compute the location of a landmark, that this means we have to maintain m tiny, small 2 by 2 Kalman filters for every landmark individually. And this would mean we would have a large, giant 2m dimensional covariance matrix using a 2m dimensional EKF. So instead of using a one high dimensional EKF, we use a large number of low dimensional EKFs. So, and therefore, this is substantially more efficient. So all these guys here are now 2 by 2 Kalman filters, so EKFs. Every landmark, location of every landmark can be easily estimated on its own, independently of the rest, given I know the poses. So every sample, because every sample says I know where the robot was, that's the assumption of each sample. Because I know where I was, I can compute every landmark individually. So every sample can maintain m small, tiny 2 by 2 Kalman filters and estimate the location of each landmark in a very, very effective manner. Okay, to sum that up, we have this posterior here, which is, of which we want to use a particle filter, and this is somehow similar to MCL, to Monte Carlo localization, because we want to estimate the trajectory of the robot given our observations, given our controls. The only difference is we don't have a given map from the beginning on, but the key trick is we can build up this map incrementally, because we have our mapping process over here, which is independent for each sample. And so every of those samples which is used to represent this posterior gets a map associated, which is built individually for every individual landmark. That's kind of the key insight here. So is the basic principle on how we're trying to tackle the SLAM problem clear to everyone? If not, please ask me now, because we'll be getting a little bit more involved within the next 1 hour. So would like to make sure that you understood the concept up to here.
Just one question.
Yes, sure.
Particle start from the same position at the beginning?
Yes, typically. So typically what you do is, if you think about a practical application, you fire up your robot and you start kind of with a local reference frame. Every particle says, okay, I'm in the robot's world reference frame at 0, 0, 0. And then we start from this point on. It's typically the way you do that. If you have a different application that you directly want to start in a global reference frame, and you have an initial belief, you can distribute the samples according to this initial belief. That's basically up to you. The standard particle filter, where you say, I don't have any external frame, I just want to estimate what the map looks like. Then you start, all particles start with the same pose with 0, 0, 0. But if you want to do, for example, you want to start giving a GPS reference frame because you want to relate the robot's trajectory directly to a map, and maybe want to exploit this map partially during the mapping process. And you have, let's say, an initial distribution about where the robot is. You can use those samples to represent this start belief. You may need more samples in the beginning, depending on how large your initial uncertainty is. But most implementations start at 0, 0, 0. But it's kind of an easy extension if you want to use an initial uncertainty. Any further questions? Okay, perfect. So let's dive a little bit into the details and start with this guy over here. how are we going to do that? So we said we want to use a sample-based representation to represent this first part over here. So this guy should be represented with our samples. So how do these individual dimensions look like? So we have a starting location x0, and this is exactly refers to your question. We typically start with 0, 0, 0, unless we have some reference to an external frame. And then x1 is the pose of the robot x at time t. x2 is the pose of the robot at time t equals 2, always the xy theta location. However, in this particle filter, we never revise the path trajectory. So we never say, okay, at that point in time in the past, I did a mistake, so I correct all the samples. That's nothing which a particle filter does. So it always takes it a step forward and estimates the next trajectory of the next position of the robot. So as a result of that, in practice, I don't actually need the past trajectory of the robot because on the fly, build a map on the fly. I'm only interested in the next pose. So I can actually, I do not actually need to maintain the previous positions where the robot was in my sampled belief. So as a result, there's in the sample set, I only represent kind of the current pose of the robot because the past is not revised. I could, in theory, let's say, dump them somewhere to disk in case I need it. Typically, implementations do that because they want to draw the trajectory in the end. But for the mapping process itself, I don't need that for the estimation problem I'm facing here. So in practice, every particle only needs to maintain 3 dimensions for the pose, and then 2 times m dimensions for the landmarks, whereas every landmark is a 2x2 common filter. So that's exactly how the first efficient implementation of a so-called Rao-Blackwellized particle filter for SLAM looked like. Every particle has an x, y, theta dimension, so current pose, an x and y and orientation, landmark 1, landmark 2, landmark 3, and these guys are my 2x2 common filters. And Mike Montemello, 2002, was the first one who actually came up with exactly this representation and with an efficient way for implementing that. So it was kind of the first implementation of a Rao-Blackwellized particle filter that could handle large maps or real-world problems. So kind of the first successful implementation. And actually parts of these slides go back to Mike in here, or some of these animations, especially this one over here. So this is an example. So these are, let's say, our simplified world with only 3 samples. In reality, of course, we have more. So particle number 1, 2, and 3. Particle 1 says, okay, the robot is here. Particle 2 says the robot is here. And particle 3 says the robot is here. And these are the corresponding landmark estimates, maps of those individual samples. And these are all these 2x2 common filters. So what happens? The robot moves. So this one said, okay, the robot moved over here. This one said the robot moved over here. This one, the robot moved over here. This new position is generated with the proposal distributions, which is equivalent to the localization problem. So I just use my odometry motion model to draw the next pose. And the next step, which needs to be done, is the sensor update. So I need to take into account my sensor information to update my belief, to compute the importance weight. How can I do that? I just, let's say, this is the observation, so 2 landmarks. And I say, okay, this robot would observe 1 landmark here, 1 landmark here. This robot says, okay, 1 landmark is here, 1 landmark is here. And this says 1 landmark is here, 1 landmark is here. So what I need to do now is I need to take into account these observations excuse me, and turn them into importance weights. You can see this important weight. We will derive it later on, why it is exactly what I will show you in a second. But you can use this kind of, if I talk quite informally about that, it's kind of an evaluation. How well did the particle in estimating the map given the current sensor observations? So how well are the current sensor observations in line with the map that this individual particle built? So if you think about over here, that actually looks pretty close. So if, let's say under the assumption that this observation corresponds to this landmark and this observation corresponds to this landmark, that looks kind of reasonable. Here we are much further away from our estimates. So this particle will get a high likelihood, and this will get a probably quite low likelihood. And this one, this landmark, this observation is pretty far away from that landmark, also will get a quite low likelihood. So this is exactly what happens. We can compute importance weights based on the maps of the samples, the locations of the samples, and the current observation. We will go into the details how this weight update looks like. And as a result, you get a weight update. So every sample gets a weight. And then the observation is used to actually update the map of each sample, because it's a new observation. And I now say, okay, the pose of the robot is here. Given the pose of the robot was here, I can actually update my map. This is exactly what happens. I do a number of small, tiny EKF updates for every landmark individually, and then obtain a new belief for that system. Yes, please.
Do I do that for every particle? This update of the whole map?
Yes, exactly.
Isn't that pretty expensive? And we could say, okay, like in this example, particle 3 is pretty far away from what we observed, and so we just calculated for the first 5 particles with the biggest weights.
So first of all, it's absolutely right. You need to update the map of every individual sample. So if you have n maps to update, it's obviously up to n times more expensive than a single map. That's true. However, if you compare to the EKF, the great advantage that we have here is that we have individual 2x2 Kalman filters. So this is a kind of a constant time operation for every landmark. We typically observe just a small number of landmarks. This is done very, very efficiently. Compared to the EKF, where we have to invert our huge m by m dimensional matrix, which is actually a more costly operation than this operation here. Of course, it depends on the number of samples. If you have whatever trillions of samples, the more samples you have, the more costly this operation obviously gets. But for reasonable sizes, this is not a limiting factor, at least for large maps. If you have a small map, the EKF may be more efficient, but if you have large maps with a large number of samples, this makes a big difference. But again, just to stress this, a substantial number of research activities in this area says, okay, how can we reduce the number of samples in order to be more efficient? So it's an absolutely valid question, but from the computational complexity point of view, we actually gain something if we do it in that way, because we only have low-dimensional EKFs and not one large high-dimensional one, and therefore I can typically easily compensate, given that the number of samples is typically constant and the number of landmarks is typically larger than the number of samples that I have. Yes, please.
So do we have a threshold weight where we say, okay, this particle is so unlikely now, we just skip it and create a new one? Or?
No, that doesn't happen at all. So okay. There's no threshold which eliminates the sample. The resampling process kind of takes care of you for that, because it draws samples proportional to its weight. So if you have a sample which is a very low weight, there's a very small probability that it is drawn and taken to into the next generation of samples. So this comes automatically just by drawing with a sample with a probability that is proportional to its weight. But it's not that we need to maintain an explicit threshold to eliminate the samples. This is not the case. Okay, any further questions? Okay, perfect. So what we have now done in the first half an hour now is kind of give you a rough idea how the EKF works. And everyone probably, the FastSLAM works. And every one of you is probably saying, okay, I think I understood that. And that's perfect. I hope that this is the case. We will dive now a little bit deeper into the math, but it should not violate the picture that you generated in the mental picture that you generated of FastSLAM right now. The only thing is what I will now do, if we dive into the details, I want to give you more detailed explanation why something is exactly as it is. So for example, this thing, how is a weight exactly computed, what we have here? Why is a weight like this? So I would kind of, after this more informal introduction to FastSLAM, I would now go deeply into FastSLAM and say, this is the result, or this is a design choice, and this design choice leads to these and these computations, which then result, for example, in this way of computing the importance weight. And that's kind of my key idea, that after this lecture, you're actually able to implement such a system yourself. That will be my goal. Okay, let's look to the key steps of FastSLAM, and we look into so-called what is FastSLAM 1, which is kind of the first, obviously first generation of FastSLAM. There's a second generation of FastSLAM. But what I explained here is something which is known as FastSLAM 1. What it does, it draws samples according to the standard odometry model that we used in localization. So it says it extends the path posterior to the next point in time by just taking every sample, and for every sample I draw the new generation according to the motion model. That's exactly the same as in Monte Carlo localization. So this first step should be kind of clear. Anyone who needs a short recap from that, how this works? Perfect, good. So we take our old generation of samples, and for every sample, we draw a new pose taking into account the odometry information. This gives us a new sample. The second step is to compute an importance weight, and the importance weight mathematically is defined as a target divided by the proposal, and it tells us how do we need to correct our belief as this guy over here, the odometry, is not the full distribution that I want to approximate, so my target is just a part of that, because I want to take into account as well as the observation. And this is something which comes in here. And so what are the individual elements here? So this is a Gaussian distribution, and what it says, it takes a current observation minus the expected observation or predicted observation. And this predicted observation is computed for every particle. As every particle has its own map, every particle will come up with a different expected observation. Compared to the EKF, where I computed one expected observation, I compute here an expected observation for every sample, because every sample keeps its own map. So for every sample, I say, how well does the obtained observation match with the expected observation? And I have a measurement covariance. The measurement covariance is something which I also used in the EKF. This takes into account the uncertainty of the landmark itself and the uncertainty of the observation. It's kind of this part in the EKF which gets inverted, this part which I need to invert in the prediction, in the correction step. That's exactly what's called measurement covariance. Then the third step is just a belief update using the EKF update rule. No black magic in here, and the standard resampling operation. Okay, so let's now dive into the detail. If you want to implement that algorithm, how does this look like? I start with my FastSLAM 1 with known correspondences. Again, that was something we assumed. We have n samples here, ranging from k equals 1 to k equals n. So we iterate over all samples. What do we do? Okay, let's say we have our individual samples. So every sample has a pose and a landmark estimate. Therefore, it's kind of a list of landmarks and an importance weight. Okay, and we have that for every sample. So for every sample, we have the current pose estimate, the weight, and a list of 2x2 Kalman filters, given a mean and a covariance, which represents the poses of the individual landmarks. This is what this guy should express here. So the first thing we do, we say, okay, given the current pose at time t minus 1 of that particle and the odometry command ut, I sample a new pose for that sample. Standard odometry motion model sampling as in Monte Carlo localization. Okay, first part was easy. This is a prediction step. Now let's go into the correction step. Okay, we assume J is kind of the feature that we observe in our current observation. This is the state association variable, which tells us just the current measurement that we take is actually particle landmark J of that particle. Same as in the EKF. Okay, again, as in the EKF, I have to distinguish two situations. First, the landmark has never been seen before, so I need to initialize it, or it had been seen already in the past. So I start with, has never been seen. What I do is, I compute its mean with the inverse of my observation function, exactly in the same way as this was done in the EKF. So if I've never seen a landmark, I use the first observation to initialize it. I compute the Jacobian, I compute its initial uncertainty, taking into account how certain am I about my observation, and the Jacobian, and I have a default importance weight, standard value, because otherwise it would be undefined. Because so this is a new landmark for every. For this sample, it's of course regarded as a new landmark. So just initialize the landmark. This was kind of just the initialization case. The more interesting case is actually when I know this landmark, when I update my landmark. So this part comes over here. So I have written it in a short form, which just says, okay, it's landmark J that we observed, so just execute the EKF update for that step. I don't need a prediction step, I only need the update step, because the prediction step of the sample is done with the particles, and just the update step for the map is done with the EKF update. And then I compute my importance weight, as I said before, with the expected observation and the measurement covariance. The measurement covariance takes into account the uncertainty that the landmark had in the previous step and the measurement noise. So how certain have I been about the estimate in the map, and plus the uncertainty of my observation. It's very similar to this term which was used to compute the Kalman gain, except that this guy got inverted in the end. Okay? And for all features that we have not observed, I just don't change them. So just say, okay, for every landmark which I have not observed, they take exactly the same belief as it was before, the case before. Okay? I iterate over all samples, and in the end I do a resampling step. That's it. Yes, please.
For all unobserved, does that mean for all unobserved in this step, or for all unobserved?
No, for all unobserved in this step. So if I don't observe a landmark, I take the previous estimate. So it's kind of, this is no black magic. In practice, you would actually implement it in a way that you update the landmarks in place, and then you don't need to do any copy operation like this. It's just kind of for writing it in a nice, hopefully easier to understand way. So there are three things. Either you have never observed the landmarks and initialize it, or you observe it, or there are landmarks which are not observed. These are the three cases which can occur, and these are handled in this algorithm. So in the next slide, oh yes, please, another question. Yeah, sure. Yeah.
In the line curve that you measure the weight,
yeah.
you measure the weight based on the old location of the landmarks or new location of landmarks, because you update them. You measure the weight, because after updating the landmarks, now the weight of the particles increases because you put it in the correct location.
Very, very good observation. It's written on the slide how this is done. If you look how Q is computed, Q takes the uncertainty of the previous point in time. So you do that before the update. So you can say, because what you do here is you say the old estimate leads to the new estimate with time step t here, but he used t minus 1. So it's a very good observation. You need to first compute the weight and then update the map. Very good observation. On the next slide, I have the same algorithm here. The only thing which I did, I expanded the EKF update. I just put that here for completeness. So if you, because this is one of the homework, will dive deeper into that implementation, at least everything at hand. So this block over here, the red block, is exactly this EKF update equation, which is over here. And this is just a copy-paste operation from the EKF. So what we do is compute our predicted observation. The only difference is we now do it for every particle. And here you exactly see it's done at the time step t minus 1, what you were referring to. So not at t minus 1. I compute my Jacobian, I compute the measurement covariance, I compute my Kalman gain. And here you see exactly that the Kalman gain take this measurement covariance inverted into account. So this was the block that I inverted the EKF. Then I update my mean estimate exactly as a weighted sum of the prediction and the kind of correction. And I compute update the covariance of that landmark. So it's just a standard copy-paste from the EKF algorithm. Okay, so we have now basically explained all the important things. The only thing is, why the hell is this the importance factor? It's something which I haven't told you at all right now. You accepted all of that, you all accepted that, but I haven't derived that. And that's something which we will do very, very soon. But before I do that, I just want to show you an example how that works. So what you see here is a simulated environment. It's a video by Mike Montemello. All the blue dots are the ground truth location of the landmarks. The blue trajectory that you will see evolve is the true trajectory that the vehicle has taken. Red is the estimate. I think the dashed line is odometry. Okay, and this part here is kind of the visibility range of the sensor. So all those landmarks is kind of after the first step. Okay, come on. No. Mouse cursor is gone. Oh, here it is. Okay. So you see how the red and the blue, they are both more or less on top of each other. Sometimes you see a small deviation. This is kind of the difference between ground truth and the estimate. You always see the estimate of the best particle, which is shown here. And the dashed line here is odometry. It's kind of just be a small illustration to give you an idea how this EKF works. And you see sometimes these red dots which flicker around. These are the observations that the system took. Yeah, like these guys over here. These were the observations, in this case, for this landmark and for this landmark over here.
What was the dashed line?
The odometry. If you would just take into account, just rerun it. Okay. If you would just use the odometry information, that will be the estimate that the system would be. So you can see here it deviates from the true trajectory. Yeah. Okay, so now let's look into the last thing which I promised you. Why is this term which I showed you actually the importance weight? The importance weight, as I said before, is a direct result of the importance sampling principle. So the importance sampling principle says I can draw samples from an arbitrary distribution, basically arbitrary, some small constraints, but for us, let's say arbitrary. And then, although I want to represent a different distribution, and then I need to correct each sample by assigning it a weight, and the weight is given by the ratio between the target distribution, so the distribution I want to approximate, and the proposal distribution, which is a distribution from which I've drawn my samples. This is exactly what is shown over here. What I now want to do is I want to start from this equation and tell you I have a certain target distribution which I want to approximate. I use a certain proposal distribution. We'll do some derivations, and then in the end, this equation which I have shown should evolve from that. Okay, so my target distribution is the trajectory, the path of the robot given the observations and given the control commands. Right? That's what I wanted to approximate. The proposal distribution takes into account all the information except the last observation, because I don't take into account my sensor observation when I draw the samples. I only use odometry information. And I say the proposal is used by a step-by-step process. So I have some kind of recursive belief which I use, and I evolve the samples according to this equation. So I said I take the belief at the previous point in time. This is kind of this recursive part here. I take the odometry and propagate that forward. So I can write my proposal in this way. Is that clear? So is everyone clear that this is the target distribution? That's what we wanted to represent with our samples. The proposal is this guy over here, which says, and it's kind of split up into two parts. This is the direct odometry motion model, so kind of one step ahead. And this stuff this is kind of what comes from my previous belief. Right? So this is kind of the part which is equivalent to this term up here, except that all the time indices are -1. So that's kind of what my previous belief was. So I want to take my previous belief and take it a step further. Okay, so let's simply go like that. We say, my weight is my target divided by the proposal distribution. So just put in these terms. That was my target, that was my proposal. I have this index k over here because I evaluate my target and my proposal exactly in the location which was drawn, for which the sample was drawn. Okay? So I have this equation over here. What I continue to do with that, I take this equation over here, this part over here on top, and just apply Bayes' rule. So I say, okay, I go this, I apply Bayes' rule, and do a factorization. So I end up with this term over here. So it gets a little bit messy. But actually, everything is pretty straightforward if you know Bayes' rule. So what happened over here? We moved zt to the other side. So zt moved over here, and all the poses moved over here. So we have p of zt given all the poses times the what is this? The poses, that should be, no, times all the poses. The only thing I did here, I just factorized it. And all the poses can be factorized in the current pose, given the previous pose, and the belief about all previous poses. So it's like p of x1 to t is p of xt given xt minus 1 times p of x1 to t minus 1. Right? This is just standard factorization. And here, using the Markov assumption, otherwise I would have 1 to t minus 1 here. This is just standard factorization, and this is exactly what is done over here. So this term, the second part of the Bayes rule was all poses from x1 to t, which is here split up in xt and all the previous poses. And I have my normalizing term, of course, over here from Bayes rule. That's it, what happened so far. And now you can see we can easily simplify this. These two guys are exactly the same, right? And these two guys are exactly the same. So perfect, we can get rid of all of them. And so the only thing which remains is my normalization constant, which needs to make sure that the weights of all samples sum up to 1. And this term over here. So the likelihood of the current observation given all the poses and the past observations. Okay? Okay, let's take this term and take it a step further. What I can do in here is I can integrate over the position of the observed landmark, like the marginalization step rule from which this. So I introduce the position of the landmark j, so the landmark that I observed. I get this term over here. So here mj, here sits mj is given, and then mj given all the rest. Right? Okay. Now I can look to this to these terms and say, okay, given I know the current pose of the system and given I know where the landmark is, I can get rid of all previous poses and all previous observations. So it's exactly the same assumption we did in whatever Monte Carlo localization and all our models is. Given we know the state, so given we know where the landmark is and given we know where the robot is, we can compute the likelihood of an observation. So this term simplifies to exactly this equation over here. And the second term remains as it is. The only difference is here I get rid of the xt because if I say if I only have observations up to t minus 1, I don't care about where the robot was in the future in order to estimate the location of a landmark. So just if I know where the robot is in the future, doesn't help me to estimate the position of the landmark. Also a step we have done in the past quite often. Okay, so what do we have in here? What we have in here, what is this? Which problem is this one? Estimating the location of a landmark, single landmark, given our observations and given the poses. Mapping with known poses. So this is our 2x2 EKF which we can use to compute that. So it's a Gaussian which we know how to estimate. What we have here is the likelihood of an observation given we know the poses and given we know the landmark location. Again, we go back to the EKF, how we done that in the EKF. We know that's all quite easy. And under the assumption that this is kind of a Gaussian, that we use a Gaussian model, this is the likelihood of the current observation given the predicted observation and the uncertainty of that observation. Exactly the same as in the EKF, right? Where we use this to kind of trade off for computing the Kalman gain. And the second thing, what is down here is just the estimate of the location of the landmark given the terms from our what we computed with the EKF, our EKF estimate. And as a result of that, I can combine that as the measurement covariance matrix Q, which is given by the previous estimate. This is just the Jacobian of the observation, plus the measurement noise. So, okay, this is the uncertainty of this belief up here. This results in a Gaussian distribution where this Q is exactly this measurement covariance, and here the predicted observation. The only thing I have in here says this is an approximation, it's not exact. And the reason why this is not exact is because there's a linearization involved so we again have to linearize my observation function if I do it in that way, similar to the EKF. So as a result, the importance weight can be computed by evaluating the Gaussian distribution and comparing what's the difference between the current observation and the predicted observation, given the expected uncertainty of that belief, which is given by how certain am I about the location of the landmark and plus the uncertainty of my sensor. So this perfectly fits with the intuition I said before in the beginning today. I say the weight tells me how consistent is the map that the particle built with what the robot currently sees. This is exactly what's written in here. This is what the robot currently sees. This is what the particle estimated. And in here is also encoded the sensor noise and the uncertainty of the estimate of that particle. So the weight tells me how consistent is the world representation that the individual sample generated with what the robot physically perceives. And the closer the expected observation is with the observations the system obtained in reality, the higher the weight. So the better the model that this particle built, and the better the pose estimate of that particle in turn. Okay? And this is the reason why in this algorithm we have this line over here on how to compute the weight. That's it. That was all the black magic involved in FastSLAM. So to summarize, the key design decisions have been we take the proposal as a proposal distribution my odometry motion model. As a result of that, of this design choice, I need to compute the weights according to this distribution. And as the landmarks are independent of each other, given I know where the system was during the mapping process, I can use small, tiny 2x2 Kalman filters, or extended Kalman filters, to represent the location of the individual features for every single particle. And this is this EKF update step, which I then do. And this is kind of the whole magic of basic FastSLAM 1.0. Is there any question I can answer you right now from that? Okay.
Maybe.
Yeah, sure.
How do you get rid of the integral? I didn't get.
So what you see in here is it's a mixture between two terms. So you have in the end it's a convolution of a Gaussian distribution where you have an estimate and you have the uncertainty of the observation. And this is a convolution of the Gaussian distribution with the Gaussian, which is Gaussian again. And that's the way how this results in that. So that's kind of the reason why you can show that under the assumption that these two guys are Gaussian, the result is a Gaussian again. But very valid question. Okay, so now let's look into one thing which we ignored so far, but this is, or for the EKF at least, we said we assumed we have this data association. So we assumed we know the data association, this C, correspondence variable C was given. So we knew which observation corresponds to which landmark. How do I actually do that in practice? And if you see this example over here, let's say this is where the robot thinks it is. These are 3 landmarks in the environment. These are the observations. So the robot could say, okay, either this guy goes here or goes, so corresponds to this landmark or to this landmark, and the same here. And kind of, if this one should be this landmark, it's quite likely that this one will be this landmark. But in theory, you have all possible assignments of observations to landmarks. And the problem is there's a large number of possible data associations, and the number of possible data associations depends on the pose of the robot. So if I would know that the robot was sitting, let's say, over here, a little bit rotated to the right, it's quite likely that the kind of red association would be the most likely, or at least the most likely one. If the robot was sitting a little bit more to the left, rotated to the left, the blue one is likely to be the correct one. So the pose of the robot influences the data association. And this is now a great advantage for the FastSLAM algorithm. And the reason is that I can do my data association on a per particle basis. Every particle can make a different data association. And if a particle does good data associations, it's more likely to survive the resampling steps compared to a particle which does bad data associations. So the big advantage is now, if the robot is sitting over here and observes 3 landmarks, it's quite likely that this is the data association that it does, that it did. If the particle sits down here, it's quite likely that this is the data association. And particles here in the middle would get a lower weight because they don't fit to any of those constellations very well. And this is one of those situations where you quickly get a multimodal belief. So it says the robot went either here or here because both observations fit very well with the pattern of landmarks that I see. So I will end up in multimodal beliefs, so not this kind of nice banana shape or Gaussian distributions as seen over here. And this is one of the advantages of the particle filter, that I can do the data association on a per particle basis. Another example is this example over here. So the robot sits over here. These are 2 landmarks in my map, and that's the observation that the robot gets. And the red or the brown landmark. What I can do now, I can just compute the Mahalanobis distance of the expected observation with respect to those 2 landmarks over here. And this may result in the case that, okay, with probability 0.3, it's the red one. With probability 0.7, it's the brown one. What should I do? The standard approach is, okay, just take the most likely one. But what I can do now here in this situation, I can actually sample it. Just say, okay, I don't know which one it is. I just draw with one landmark with a probability that is actually given by the individual probabilities. So if I would sample here 10 times, 7 times I would draw the brown data association, 3 times I would draw the red data association. And if I have a large number of samples, I can just sample those data associations. So some samples will draw the right data association, some samples will draw the wrong data association. As a result, they will come up with different maps, and at least the hope is that in the long run, those which did the right data association survive, and those which did the wrong data association die out. Of course, this process may take some time. I need to have a sufficient number of samples to cover all the different possibilities, but the particle filter has these possibilities. So, yeah, there are, as I said, multiple options. One is pick the most probable match. That's what the standard EKF would do. But again, I can pick a random data association and weight it with the probability that is the right or wrong data association. Exactly what I explained before. And what I typically have, I have a threshold. If there's no landmark which has a high likelihood of being a association, I assume it to be a new one. But again, that's an assumption. So the nice thing in here is that this is a very easy strategy. It's very simple to implement, but has very nice properties. And this is one of the advantages of the for FastSLAM compared to EKF, that I can do very simple but effective data associations. And the reason for this is that I don't have a parametric form which describes the uncertainty of the robot. I have this sampled belief. In this sampled belief, you can say, okay, for this sample, this is the right data association. For this sample, this is the right data association. And this sampled representation makes it very, very easy for me to make this advanced data association, having multiple data association possibilities in my belief. This is something which naturally evolves from FastSLAM, and the advantage here is the sampled belief compared to a whatever Gaussian distribution or other parametric form that I have. And this is kind of one situation where the sampled belief is really, really advantageous and offers me a nice possibility to do that. Okay, let's see how this this FastSLAM actually compares to this Victoria Park data set. You have seen that. There's just one example where you can then use the GPS information to analyze the error. Again, you see it's not a perfect estimate, but it's typically better than what the EKF provides. Also a small video where you can again see that. Again, it's a video of Mike, provided by Mike. So you can see the robot driving around here. These red dots are the observations, also the uncertainty of the observations in the model. Blue is, in this case, the odometry, so it's not the ground truth information. So a little bit inconsistent in the coloring for the video. Sorry for that. And so the red trajectory here is the trajectory of the FastSLAM algorithm. At least you can see that using odometry would give you a pretty inconsistent estimate. At least something you should see from this plot over here. Okay, that goes on for quite a while. One thing one should analyze is which impact does the sample size have on this algorithm. Because obviously, if you just take, let's say, a single sample, you're quite likely to perform poorly. How does it change with 10 samples? How does it change with 100 samples? So typically, the higher the number of samples, the better is your estimate. And what you can see over here is if everything is perfect, so this example, this was a simulated data set, everything was perfectly Gaussian, then it's just that the performance of the EKF in terms of quality of the results is actually pretty good. And this also assumes that you have a low motion noise, or at least you have a roughly linear function for your motion noise. If you now increase the motion noise of this algorithm, the results look substantially different. Then the performance of the EKF dramatically decreases because the nonlinearity in the motion kind of kicks in, combined with a large uncertainty gives you bad estimates of the pose estimate. And so the error here dramatically increases, while it basically not noticeably affects the FastSLAM algorithm. So it's an interesting algorithm which has some very nice properties. So try to get rid of the EKF to model the joint posterior. Just says, okay, I split that up with one part, especially the one which also the motion is represented by a linear function. I use a particle-based representation, so I can multimodal believe where the robot is. And then given this multimodal sampled belief, I compute a distribution over maps where I said every particle has its own map. And in this way, I can also take into account different data associations on a per particle basis, which is really an advantage if you don't have a good technique to get, let's say, a good feature descriptor, which always gives you very good data associations. As I said, it models the robot's path by sampling, so by samples. It computes the map given the path, and we can do a per particle based data association. And as a result of that, and this is the reason why the data association is simpler in this case, is that you can you don't have a distribution. So for every data association decision that you do, you don't have a distribution about the robot's pose, but you have a concrete instance. The robot was here. That was the sampled belief, and this makes it easier. Of course, you have to do n data associations for every particle, but it's much easier to do n simple data associations than one complex one where you have to reason or integrate over possible data associations given the uncertainty of the vehicle itself. Okay, the next thing I would like to do is look into the computational complexity of that algorithm. So let's have a look and analyze this algorithm. What do you think is the computational complexity of standard FastSLAM? What about integrating the odometry information? How complex is that in terms of number of landmarks and number of particles? Exactly. So it should be
linear the number.
Exactly. It's quite likely to be linear in the number of particles. Absolutely right. What about the landmarks? Does it depend on the landmarks?
The odometry does not update. Does not.
Perfect. So there's no dependency on the landmarks, the motion step. So it should be just linear in the number of samples. What about integrating the observation into my belief? Why n times m?
Because each particle has to not n because n not observed particle. Just n number of observed particle.
Okay, so observed. You mean?
Observed landmark and then multiplying with the particle.
Okay, so the number of particles times the number of observed landmarks. If we assume we do every landmark separately, it's absolutely right. We have the number of it's linear in the number of particles because every particle needs to update. I have the data association, so I just basically look up in an array of, this is landmark number 10, so retrieve landmark number 10 and update. It doesn't depend on how many landmarks I've stored there, if I implement in that way. Resampling. How expensive is resampling? So how expensive was this low variance resampling, which I explained last time? It was linear in the number of samples. But, there's a big but. So the resampling procedure itself is linear in the number of samples. But in the worst case, I need to copy the samples, duplicate a sample. And duplicating a sample means copying the map. And so the resampling step now turns out to be the most important, computationally most demanding operation in the standard simple particle filter based implementation because it's the number of particles times the number of landmarks. Because maybe if all particles have a weight close to 0 and one has a weight close to 1, it's quite likely that this particle will be copied n times, and then I have an n times m computational complexity. So this is kind of the computational complexity for every iteration for a simple implementation of FastSLAM. Still, it's just linear in the number of landmarks, which is actually quite remarkable if you compare it to the EKF. But we can do better. We can do better by not changing the algorithm, but just by using a smarter data structure. Instead of saying, okay, every particle maintains its an array, let's say, where it stores all the, or list where it stores an array, where it stores all the landmarks. I take a smart tree structure, a binary search tree, where particles can share landmarks. As the landmarks are all independent of each other, if I update some landmarks in this part of the state space, I typically don't change the landmark somewhere else. It's not as in the EKF where an update here can change the uncertainty of all landmarks everywhere. There's something which I don't have here because I have this conditional independence given the poses of the robot, so given the sample. So what I can do is I compute, I take a search tree, it's not a simple search tree, and so just say, okay, I'm looking for, let's say, the landmark number 3. So So take a search tree, okay. Is it smaller than 4? Yes, I go here. Is it smaller than 2? No, I go here. Is it smaller than 3 or smaller equal 3? Yes, I found my landmark number 3 here. It's just a binary search tree. No black magic. Every one of you should have heard that in Introduction to Computer Science 1 or Algorithms and Data Structures. So, and this has a complexity which is logarithmic in the number of landmarks that I have. So I can access a landmark in a logarithmic complexity. What I now can do is, I can say, okay, now let's do exactly the same thing. Let's particle share those estimates down here. And then the tree gets a little bit more complex. So say I have my old particle. So this was at the previous point in time. And I have a new particle, which comes, let's say a particle is duplicated from the resampling process. Gets a new particle. Then I can build, for the old particle, I can build, have my standard tree as it was the case. And for my new particle, it references into the old tree. And whenever something is updated, just this updated path is replicated and then stored locally. So only if I update a landmark, and this is a constant number of operations I do every point in time, I need to kind of store here now 2 different estimates of landmark number 3, but all the rest is shared. This requires some bookkeeping to do that, what has been updated, to which particle does this estimate kind of belong to, but you can, in this way, can do that that copying can be done very efficiently, and then the only thing is that retrieving a landmark, it's a complexity which is logarithmic in the number of landmarks and not constant anymore. As a result of that, this step, integrating an observation, gets more expensive. It gets the factor log m. But the resampling gets cheaper, and so the overall complexity is cheaper. It's the number of landmarks of particles that I have times the logarithm of the number of landmarks that I need to maintain. So this is, of course, a computational complexity. Memory complexity is larger because I still need to, of course, maintain all landmarks. You had a question?
No, I only had a mistake on the last slide. I think on the right side we have the same as on the left side. In the last line with the J, it's 1 and 3 on the right side.
Yes. So this is definitely a copy-paste error when making this figure. So this should be 5, and this should be 7.
Yeah.
Absolutely right. 5 and 7. Yep. Okay. Let's look to the memory usage of this algorithm. And so the memory usage is dramatically reduced for using this smart tree structure because you don't need to replicate the number of the landmark estimates for all particles. And you can nicely see that kind of the log n complexity is here along these lines, and the linear FastSLAM, which copies for every particle the number of landmarks, has a complexity which grows linearly with the number of samples, and kind of how steep this increase is just only depends on the number of particles you have, because the number of particles is constant. And so if you have more particles, you would have a steeper increase here, but it will be still linear. Okay, so that was kind of FastSLAM 1. Now you know everything about FastSLAM 1. And I just want to use now the next 2 to 3 minutes to explain to you what FastSLAM 2 could be, or at least tell you what the improvements will be, because then in the next lecture we will look into how to build maps with kind of with grid maps with these particle filters, and then we actually look into kind of FastSLAM 2 for grid maps, because for grid maps this FastSLAM 1 doesn't really work for some reasons we will explore next time, but for landmark maps it's operational, it works, but FastSLAM 2 for grid maps is then the solution. Therefore I said, okay, I don't go into FastSLAM 2 for landmarks, just do FastSLAM 1 for landmarks, and we do FastSLAM 2 for grid maps next week. But at least I would like to give an idea how we can do better. So what FastSLAM 1 does, it says, okay, we take as our proposal distribution our odometry motion model. And the question is there a better way to do that? Obviously, if I ask such a question, there is a better way to do that. How could you imagine a better way for doing that? How can you do samples better? Better means that you draw the samples only in the kind of high areas of high likelihood or regions of high likelihood of your state space. There's a technique we discussed last week which may help to inspire you in doing that. The end of the grid mapping chapter. Scan matching, maybe? Okay, so the idea was to, if we have an accurate sensor information, just by aligning sensor scans, like laser range scans, we actually get much better pose estimate than comparing just using the odometry information. So what FastSLAM 2 does, it also considers the measurements in the proposal distribution. This kind of breaks a little bit with this clear correspondence from this particle filter implementation to the standard base filter, where you say we only take the control for the prediction step and only take the observations for the correction step. So this kind of mixes those two steps a little bit more together, because it says, okay, we also take into account our observations for already sampling our particles. So we compute a better proposal, and better means here a distribution which is closer to my target distribution. So more samples will end up in the likely areas of the state space, and much fewer samples will end up in low likelihood areas. And this is kind of the key step to bring this algorithm to the next level of performance. So what FastSLAM 2 does, it draws from a proposal distribution which also has all the odometry all the sensor information in here, right? And this leads to be in proposal distributions which are much more peaked around the true state where the system is in, not these kind of flat, large distributions. So as a result of that, I need less samples, therefore it can be computationally advantageous. On the other hand, I have to say that the computations for this proposal are more involving, and then you may argue that the gain that you get by reducing the number of samples, at least in the computation time you need, may be gone, but you get much more peak distributions, and this leads to a higher likelihood that your filter will not diverge and get good estimates, especially in the long run. That gets more complicated. There's something which is known as FastSLAM 2, which we don't go into the details here for feature-based FastSLAM, but we do that next week in the context of grid-based FastSLAM, where we will look into this problem again. Just as a small comparison, how is the performance between FastSLAM 1 and FastSLAM 2? So it's just a small example. A robot was driving around here. This is FastSLAM 1. FastSLAM 2, you see, looks actually not too different the first round. But what you can see is here that these particles have a much longer history, so I have a much larger diversity of trajectory estimates in the past, whereas the FastSLAM 1, down here, if all particles have basically the same estimate, only from this point in time on, they kind of spread out a little bit. And this is the reason that the frequent resampling steps eliminate particles. And if I continue eliminating particles, always a substantial number in every step, I kind of eliminate different trajectory hypotheses in the past, because all the particles are kind of replaced, and then kind of information about the past die out. As a result of that, this FastSLAM 2 has a higher diversity of estimates, because they all are good estimates. Here we just kind of converge to one mode, so to say. This one is more likely to maintain multiple modes, and this is substantially better when you close large loops, or because then multiple hypotheses about how the trajectory looks like in the past make a big difference. But maybe just kind of, this is just as a teaser. We will dive into this into next week, and then you will, let's say, get a bit more knowledge about what's going on, why this is an important property of these algorithms. So to sum up with FastSLAM, what does FastSLAM typically refer to? FastSLAM is particle filter-based SLAM that uses this trick of separating the estimation of the trajectory from the estimation of the map, by saying we use particles only to estimate the trajectory, And then for every of those trajectory estimates, so for every particle, we build a known map. This is something which is called Rao-Blackwellization. And therefore, it's a kind of a Rao-Blackwellized particle filter for SLAM. And using this with landmarks, is Mike Montemello coined this term FastSLAM. And there's FastSLAM 2 and FastSLAM 1. And the main differences between FastSLAM 1 and FastSLAM 2 that FastSLAM 2 uses a so-called improved proposal distribution. So a better proposal distribution which takes into account also the most recent sensor observation in order to have a more peak distribution around the areas of high likelihood. In terms of computational complexity, FastSLAM is a pretty nice algorithm in the sense that it is logarithmic in the number of landmarks that I have and linear in the number of samples. And the number of samples is typically constant. Let's say it could be 1,000, could be 2,000, but they are not typically do not grow excessively. Okay, FastSLAM have been shown to actually work quite convincingly. So it scales very well to millions of landmarks. So there have been data sets with at least 1 million of landmarks using FastSLAM in order to solve this problem, which gets pretty tricky for EKF, because you would have a 2 by 2 million landmark covariance matrix. You need to invert matrices of this size. It can be ugly. No, you don't need to. That was wrong statements. You don't need to invert them, but you need to multiply those matrices, so you have at least a quadratic complexity that you need to maintain for the EKF. And here we only have a logarithmic complexity, so this is substantially better. Logarithmic is substantially better than quadratic if you compare both. The other advantages of the FastSLAM algorithm is that you have quite some flexibility in doing data association. You can do per particle data associations, and this is kind of a really nice property and makes it solving the data association problem easier. And it has a further advantage, which I haven't discussed in detail here, but the reason, or the linearization of the motion model, where the EKF suffers from, is not a problem for FastSLAM, because you just propagate a point through a nonlinear function, namely the pose of the particle. Of course, you still need to sample around that, but it's less critical to have, if you have nonlinear motion models, because you can propagate them in a much better way. You do not necessarily generate a Gaussian estimate. So of course, you need to have a way for sampling from these distributions, but you're not restricted to linearization and a Gaussian approach. If you want to know more about FastSLAM, again, I recommend the Probabilistic Robotics book. In this case, see the errata page, because the printing of the book has still a couple of errors. I hope to have fixed all the errors on the slides here. That's kind of probably the reference which is easiest to grab. Here are kind of two papers by Mike Montemello, the 2002 and 2003 paper, where he introduced FastSLAM 1, one with known data association, the second one with unknown data association, which are really nice works. I guess the first one is easier to grasp, easier to understand, so I would recommend looking into this one. On the other hand, those you find for free on the web. If you don't have the book, you don't want to buy the book, and you don't want to read in the library, you may also have a look to these two works. That's it from my side for today. Are there any questions? Okay, good. So we close features for now. It was kind of the last, at least for some time, the last landmark-based approach that you have seen, and we look into the grid-based mapping techniques using Rao-Blackwellized particle filters next week before Christmas, and then also look into kind of this FastSLAM 2, or kind of FastSLAM 2 ideas but applied to grid maps, and then we'll have a long Christmas break, and then next year we will look into the graph-based approaches of the simultaneous localization and mapping problem. That's it from my side for today. If there are no any questions, then thank you very much, and we see each other next week. Bye-bye.